Okay, so in this video, I'm going to finish section 5.5. And just to recall where we were in the last video, I had left off from talking about how to find vertical asymptotes and then how to know what the function is approaching as x approaches the vertical asymptotes based on their multiplicity. So now we're going to be talking about how to find a horizontal or oblique asymptote of a rational function. So if we have a rational function, p of x over q of x, just note that this can also be written in its polynomial form, where you have the polynomial in x as the numerator and a polynomial of x on the denominator. So in this notation here, and I'll erase this, the n on top is the degree of the numerator, and the m is the degree of the denominator. So it's the highest exponent in the denominator is equal to m. Okay, so this is important because we're actually going to use these degrees of the numerator and the denominator to determine the horizontal asymptotes. So there are three cases. The first one says that if n is less than m, so if the degree of the top is less than the degree of the bottom, then we have y is equal to 0 will be the horizontal asymptote. So the way I remember that is if you have a small degree on top, then you have a small horizontal asymptote, y equals 0. And that's the line, the horizontal line, y equals 0. But if m is equal to n, so if the numerator and the denominator have the same degree, then the horizontal asymptote will be the equation y equals a sub n over b sub n. So what that means is whatever the ratio of the coefficients here is equal to, then that will be the horizontal asymptote if the degrees are the same. So I remember that as if the degrees are the same, then the horizontal asymptote is exactly the same as the numbers you see in front of the leading terms. And then finally, if the top degree is larger than the bottom by 1, then we will have an oblique asymptote, and it will be in the form of a linear equation, and we can find that by doing the polynomial division of that rational function and finding the quotient. So the oblique asymptote will be equal to the quotient found by doing that division. Okay, so 3 rules that we just have to follow in order to find the horizontal asymptote. So if that top degree is bigger than the bottom by more than 2, or 2 or more, then we will have no horizontal or oblique asymptote. And then we can make the conclusion that the end behavior of the graph will resemble the power function, which would be the first leading terms. If we go back here, it would just be this part right here was what they're talking about. Okay. All right, so let's do an example. So this one says to find the horizontal asymptote if one exists of this graph, 3x to the 4th power minus 2x cubed minus x all over x to the 6th plus 4x squared plus 8. So we are just trying to find the horizontal asymptote here. So we are going to look at the degrees of the top and the bottom. So on the numerator, we have the highest exponent of 4. So the degree is equal to 4 on top. And on the bottom, we have 6. So the degree is equal to 6 on the bottom. And so based on our rules, we have that the degree on top, degree of the numerator, is less than the degree of the denominator. 4 is less than 6. So if we go back to our rules, that is going to be the first case. The top is less than the bottom degree. So therefore, our horizontal asymptote is equal to y equals 0. Okay. And I will say that this is case number 1. Okay. All right, next one. We have 2x cubed plus 3x squared plus 2 over x squared plus x plus 1. So the degree on top is equal to 3. And the degree on the bottom is equal to 2. So we have that the degree of the numerator is greater than the degree of the denominator. Degree of the denominator by 1. So that is that case of the third case. So n is equal to n plus 1. That means that the top, which is 4, is equal to the bottom, which is, oh, sorry, wrong one. The top, sorry, which is 3, is equal to the bottom, which is 2 plus 1. So that is true. So it just means it's greater than the denominator by 1. So when this is the case, then we have a oblique asymptote, so no horizontal asymptote. And I will say this is case number 3. So we have no horizontal asymptote, but we do have an oblique asymptote. Okay. All right, and then to find this oblique asymptote, we will go to the next page. And let me write that down. Okay, so to find an oblique asymptote, we just figured out that we did have one. We're going to use long division. So this is 2x cubed plus 3x squared plus 2 divided by x squared plus x plus 1. So I will have my 2x cubed plus 3x squared plus 2 underneath my long division symbol. And the x squared plus x plus 1 will go underneath. Now you can put a 0 marker here in between 0 and 2 since I don't have an x term. But really when you're doing long division, it doesn't matter a whole lot. And you can also do this using synthetic division, whichever way you like to do it better. Oh, I'm so sorry. I misspoke there. you cannot use synthetic division because we are not dividing by a linear factor. This is not linear, so you have to use long division, polynomial long division. You can only use synthetic division when you are dividing by a linear divisor. Okay, so back to this. So to begin long division, I'm going to divide that 2x cubed by x squared first, and that will give me 2x. And then I will multiply 2x by all of this, and that will give me 2x cubed plus 2x squared plus 2x. And then I will subtract. So the 2x cubes will cancel. 3x squared minus 2x squared will give me 1x squared. 0 minus 2x will give me negative 2x. And then I will bring down the plus 2. And then I will repeat and divide x squared by x squared. First term there. X squared divided by x squared is 1. So this would be plus 1, positive 1. Multiply the 1 by all of this. So I get x squared plus x plus 1. And then we subtract. And so x squared minus x squared is 0. Negative 2x minus x is negative 3x. And 2 minus 1 is 1. So this is my remainder because I don't have anything else to bring down, and x squared doesn't divide into negative 3x. So the quotient here, this is where I get my oblique asymptote. And it's given by the equation y equals 2x plus 1. Okay, so oblique asymptote, our graph it may intersect it or it may not. And this is a line that goes through the y-intercept of 1 and has a slope of 2. If you remember, let me rewrite this. We can write this answer based on that division algorithm. We know that 2x cubed plus 3x squared plus 2 is now equal to x. Sorry. Oh, why did I do that? No, let me do this. Okay. Okay, that polynomial divided by x squared plus x plus 1 is equal to 2x plus 1 plus the remainder, which is negative 3x plus 1, over the original divisor. So that's equal. These two are equal to each other. It's what we just showed. And this is our quotient, and this is our remainder, and that x squared plus x plus 1 was our original divisor. Okay. So since these two equations are equal, we can kind of look at the end behavior. So if you look at just the second piece of this result, that's the remainder divided by the original divisor, we see that as x approaches infinity or negative infinity, the only thing that is actually going to matter, if I plug it into here, is going to be the first terms in the numerator and the denominator, because that plus 1 is not going to affect my result if I plug infinity, and neither is that x. So we're just talking about the end behavior here. So just remember the end behavior of the top is the leading term, the end behavior of the bottom is the leading term. So the end behavior of the entire thing would be just the ratio of the leading terms. And then x divided by x squared simplifies to 1 over x, so this is equal to negative 3 over x. And we have already seen that as x approaches infinity in the denominator, that this will go towards 0. So as x approaches infinity, this whole thing will go to 0, so therefore my graph will go towards that 2x plus 1, which is that oblique asymptote. And with these asymptotes, these functions are usually going towards these asymptotes. So that makes sense. Now in this graph here, we see that in blue, they have the original function that we started with, and they are showing us some output values for certain x values. And then in red, this is the oblique asymptote function, the 2x plus 1. So you can see that those values are getting extremely close to each other, if not equal, as x gets larger or smaller, going towards positive infinity and negative infinity. But you see that they're almost equal. So the end behavior of this entire graph is really that line 2x plus 1. And we can see that more visually here. So in red in this picture, that is the graph of the 2x plus 1, the oblique asymptote. And in blue is the function, the original function that we started with. So you can see that as x goes towards the right, these are going to start getting really close to each other, and as it goes to the left towards negative infinity, those endpoints will start getting close to each other. So as x goes off in the positive or negative direction, this graph will go towards that line 2x plus 1. That is what this says. Okay. So the next one, we are going to find the horizontal or the oblique asymptote for this function r of x. So if we look at the degrees again, we see that their degrees are actually the same. So that is going to be case number 2. And that rule says that, so these are the same. So when they are the same degree, then the horizontal asymptote, which I'm just going to use h dot a now, this will be equal to y equals, so same degree will be the same thing that we see right in front of those two leading terms, which is 9 over 3. So the horizontal asymptote is equal to 9 over 3, which is just 3. Okay. Okay, so let's see why that horizontal asymptote equals the ratio of the leading coefficients. So we will investigate the end behavior of this function as the x goes to negative infinity or positive infinity. So when the values of x get very large, the numerator of the function can be approximated by the power function, 9x squared. So as x gets very large, and we're plugging large values in for x there, the rest of this just won't really matter. Because if I have infinity squared, that's infinity times infinity, and then I try to subtract infinity, infinity times infinity is going to be an insane number. So the rest of these small values just don't matter. And then on the bottom, as x gets very large or very small, negative infinity or positive infinity, again, the -2 here will not matter. So the end behavior of this graph will go towards just the ratio of the leading terms. And since the degrees are the same, x squared divided by x squared is just 9/3, which is 3. So the end behavior of this graph should be going towards the y value of 3. And that's why we have a horizontal asymptote. Okay. Next example. This one we're looking at the degrees again. So the top one is the degree is equal to 5, and the bottom, the degree is equal to 3. So in this case, the top is greater than the bottom, but it's greater than more than 2. So it's not just greater by 1. So this is going to be that last case where we have no horizontal asymptote. And I guess I can say degree of numerator is greater than the degree of denominator by 1. So when it's greater by 1, I'm sorry, it's greater by 2. So whenever it is greater by 2 or more, this is that case where we have no horizontal asymptote and no oblique. So neither. So to see why this is the case, we will investigate the end behavior of g as x approaches negative infinity and positive infinity. So again, same reasoning. If we look at the numerator here, as values of x get very, very large, the end behavior will tend to go towards that leading term, 10x5, that power function. And then on the denominator, the end behavior will go towards that power function of x cubed. Was that supposed to have a 2 there? The very large numerator of g can be approximated by the power function, and the denominator by the power function I'm not sure where they're getting this 2 from. Right here. I feel like it shouldn't be there. So I'll have to come back to that. The graph will be like, and they even have it graphed there. Okay, well, I feel like this 2 is not supposed to be there because there is no 2 there. So I feel like this is supposed to be not there, which means that this would be equal to 10x squared. So this means that as x approaches negative infinity or infinity, positive infinity, our graph will have an end behavior like 10x squared. And this is not linear, so therefore that graph has no horizontal or oblique asymptote. The end points as x approaches infinity and negative infinity will behave as y equals 10x squared. That's what I believe. And so I think this is supposed to be really 10x squared, and then I don't think that they graphed it right. And I think it should have been more like upwards, like this, which would make more sense because then it would be closer to the actual end behavior of the graph. Okay, so this is just saying that the end behavior of this function will start to behave like this parabola. And we can kind of see that because if you look at the blue, these will eventually start to meet up right here and get really close to each other as x approaches infinity and negative infinity. All right, so let me pull up 5.6 and I'm going to start 5.6 in this video. Okay, and this is really just a continuation of what we've been doing, except for now we're going to focus on how to graph these rational functions using all the information we just learned. Okay, so let's just start with an example. So this says to analyze the graph of r of x minus 1 over x squared minus 9. So the first thing we're going to do is just to consider the domain to make sure we are aware of any of the undefined or the values that will make the function undefined. So of course the values that will make this function undefined are the values that makes the denominator equal to 0. So the first thing we're going to do is factor the numerator and the denominator, but only the denominator here can be factored. And then if I set those two factors equal to 0, I see that x cannot equal negative 3 or 3. So the domain is all real numbers except for those two values. Step 2 is we want to make sure we write the function, the rational function, in its lowest terms. But this is already written in its lowest terms because we factored it and there were no common factors in the numerator or the denominator. So this is in lowest terms. All right, step 3 is we're going to find the intercepts of this function. So to find the y-intercepts, we will plug 0 into the function. So r of 0. And this will give us 0 squared minus 9, so negative 1 over negative 9, which is positive 1/9. So the y-intercept would be 0, 1/9. And then to find the x-intercepts, we will set the entire function equal to 0 and solve. But really, this is the same thing as just setting the numerator equal to 0. Because to solve this, I would have to multiply both sides by the denominator so that I can cancel the denominator. So these will cancel on the right, and this will leave me with x minus 1 is equal to 0, since 0 times anything is 0. So really, when you're trying to find the x-intercepts, you just need to set the numerator equal to 0 and solve. So therefore, x is equal to 1, and so our x-intercept is 1, 0. Okay. Next step is we will find the vertical asymptotes and their multiplicity. So remember, to find the vertical asymptote, we set the denominator equal to 0. And solve for x. Okay, I'm going to go ahead and rewrite r of x as its factored version, x minus 3 and x plus 3. Okay, so we already know what will make the denominators equal to 0. We found that in the previous step. So therefore, the vertical asymptotes will be x is equal to 3 and x is equal to negative 3. So if we look at this factored form, we see that both of these have a multiplicity of 1. Multiplicity of 1. And that's odd, so therefore, you can kind of think of when we were learning about multiplicity of zeros, if it was odd, then that would tell us that it would cross over. So if the vertical asymptote has a odd multiplicity, then that tells us that our graph will be approaching positive infinity on one end and negative infinity on the other. So it's like it still is crossing over the x-axis. So here's negative 3, here's positive 3. Tells us that one is approaching positive and one is approaching negative. But we don't know really exactly which side it's doing it yet. We have to put all this information together first. Multiplicity of, so as x approaches 3, r of x will approach negative infinity on one side and positive infinity on the other. And same thing for as x approaches negative 3. Similarly, for x approaches negative 3, r of x will approach negative infinity on one side and infinity on the other. All right, now let's look at the horizontal asymptote. So we will look at the degree of the top and the bottom. So you will want to go back to the original form of this function, not the factored form, to look at the degree. So the top has a degree of 1, and the bottom is 2. So the degree of the numerator is less than the degree of the denominator. So therefore, we have a small horizontal asymptote. Horizontal asymptote is y equals 0. Okay, so we can put all this information together. We found our x-intercept to be 1, 0, which is right here in this graph. And our y-intercept was 0, 1/9, so it's like right above y is 0. And then our vertical asymptotes are at here, negative 3, and here 3. And then we can see on the right side of this graph, it's going down to negative infinity. But if I approach that asymptote on the other side, then it's going to positive infinity. Same thing with the other side. It's going to negative infinity this way, and it's going to positive infinity this way. So our multiplicity knowledge was correct. Now they are, plugging this into the calculator to get an idea of the rest of the graph. Oh, and then the other one was a horizontal asymptote at y equals 0, but it appears that our graph is definitely crossing that horizontal asymptote because we found a x-intercept. So of course it is crossing the line of y equals 0. So here is a more detailed picture of that graph with our intercepts, y-intercept, our x-intercept, our asymptotes, and our vertical asymptotes, and then our horizontal asymptote. So the other ends of the graph are kind of tending towards that horizontal asymptote, but the part in the middle will cross that horizontal asymptote. Okay, so here is a summary of everything that I just did in that first problem. So these are the 7 steps you can use and follow to analyze and graph a rational function. And I'm going to stop here, and we will do some more of these examples in class.